Hello there, and today we'll be continuing with the second part of module 5. Okay, so in this topic, since we can see arithmetic pipelining, we studied the basics of pipelining, what it is and how it works in the previous video. This video is going to focus on two different types of pipelining. The first one is arithmetic pipelining, and the second one is instruction pipeline. So let's start with the arithmetic first. So pipeline arithmetic units are usually found in very high speed computers. The basic use of arithmetic pipeline is for doing complex calculations, okay, advanced calculations for floating point operations, multiplication of fixed point numbers, and similar scientific problems basically. So what it does is it divides an arithmetic problem, any question that it needs to solve, into sub problems, okay, for execution in various pipeline segments. Just as we studied previously, what it does is it divides the problem into parts and then solves them parallelly for parallel computation. We'll see a flowchart. So basically this is for floating point addition and subtraction. Okay, when we consider floating point addition or subtraction, there is a different form of the number that is used. So for example, if we have a number 6.02 into 10 power 3, okay, so the exponent will be 3, fine, and the mantissa is 6.02, so the number that is used is considered as the mantissa. Okay, that's one thing I wanted to clear. Secondly, since we are adding two numbers or subtracting two numbers, so the exponent of both numbers is entered and the mantissa for both numbers. So we can take 6.00 and 7.00. One will have a power of 3 and one will have a power of 2. So we'll enter 3 and 2, 6.00 and 7.00. They both go to the register, and then in the first segment the exponents are compared. This happens by subtraction. So if one of the exponent is 2 and the other is 3, so we'll subtract 3 by 2, fine, and the greater number, okay, is stored as the main exponent which is chosen. So basically the chosen exponent is the greater exponent. Then the difference is sent to align the mantises. What happens is when we get the difference of 1, that means one exponent is bigger than the other. Okay, so what happens is we have 6.00 and 7.00. For example, 6.00 has 10 power 3 and 7.00 has 10 power 2. So what it does is it aligns 7.00 to match the power of 6.00. Okay, so it adds another 0 to the number. Okay, so that the exponent becomes 10 power 3, so it will become 70, fine. And then once it chooses the exponent, we go to, after aligning the mantissa, it stores it in the register and then it adds or subtracts them. Okay, we'll be adding, if we're adding, then addition happens and then it's stored here again. Both the registers are stored. At the last segment, what happens is the adjusting of the exponent. So if 3 was chosen, we will use 3 for both of the mantissas, both the numbers, and normalizing is again to set the decimal place at the right place, and finally we get the output of the addition of both the numbers. Here is an example. So we have two numbers x and y. Okay, a and b will be the mantissas, capital A and B, and small a and b will be their exponents. It could be base 2 or base 10, whatever, fine. Now these are the steps that we discussed. First we compare the exponents and choose the greater exponent. We align the mantissas, add or subtract the mantissas, and then normalize the result. Like we discussed previously, both the exponents are compared for a largest one to be chosen for the result. Okay, the difference decides how many times we shift the smaller exponent to the right. This is the aligning. Okay, and then again this aligning happens where after shifting the exponent, both the mantissas are also aligned. So if you change the power of one, then the number has to change as well. Finally the addition of both numbers takes place, and then normalization of result, which is basically setting the values together to make sure that the exponent and the number are correct, and then we get the output. We can take a normal numerical example for clarifying these sub operations. So first we have x as 0.3214 power 3 and 0.45 power 10 power 2, fine. So the first exponent is subtracted, okay, from the second. We get 3 minus 2 as 1, thus 3 becomes the result, which is because 3 is greater. Okay, and the smaller is shifted one time. Okay, now this is the normalization. So we shift the mantissa once towards the right, and then the exponent is increased, thus giving us the same exponent in the result as the greater exponent. Finally, we add both the numbers and we get the output. Okay, both of them are aligned together. The normalization usually happens since it's already normalized over here. We can see that the power and the mantis are both in the same uh, I mean they have the same values, so normalization gives the same result. Hence we do not need to normalize over here, but sometimes when we do need to normalize is when it is not adjusted properly. Okay, so then normalization is done by shifting the mantissa again to the right and the incrementation of the exponent. So if it's a 2, then we shift the mantissa and it becomes a 3. It has to be the same as the greatest power. Now next, the instruction pipeline. Since we saw the arithmetic pipeline is basically for performing complex computational problems such as multiplying, dividing, addition or subtraction, the instruction pipeline has to do with the instruction stream. Okay, so pipelining can occur not only for data streams but also for instruction streams. Fine. The function of an instruction pipeline is to read conservative instructions from memory while previous instructions are being executed in other segments. Again, this is a topic of parallel computing. So what we see is that since each computer has multiple instructions that it needs to perform, right? What this pipelining does is it reads the first instruction, it is executing the first instruction, and meanwhile it's being executed, it reads the next instruction. Okay, so this causes the fetch and execute phases. As we've studied in the instruction cycle, we have the fetch phase, then we have the decode and execute phase. Okay, in this pipelining case, the fetch and the execute overlap, okay, thus giving us simultaneous operations. This is the parallel computing of instructions. So we have instruction 1 that says add, instruction 2 that says divide. Fine. So when instruction 1 was read, okay, at the next clock cycle it will be executed, but while it's being executed the system goes to read instruction 2, so it reads that we need to divide, okay, while the first instruction is being performed. So one possible deviation associated with such a scheme is that an instruction may cause a branch out of sequence. What does this mean? This basically means that when an instruction is being executed, sometimes the previous instruction is dependent on the next instruction. Okay, in case this happens, what the pipeline does is that it must be emptied, okay, and all the instructions that have been read from memory after the branch instruction must be discarded. So if we have instruction number 2 for example, that depends on instruction number 3, fine, so all instructions that have been read, for example while 2 is being executed, we will understand that it is a branch instruction during the execution. Okay, so instruction number 3 would have already been read during that time. What we're going to do is we're going to discard instruction number 3, okay, and we are going to execute instruction number 2, which is the branched instruction, completely. Okay, and then the system will carry on in the way it does. Okay, here it is. So in this, a stream of instructions can be executed by overlapping fetch, decode and execute phases of an instruction cycle. This is used to increase the throughput of the computer system. Basically it increases the output and the efficiency of the computer system by performing multiple instructions parallelly. An instruction pipeline reads the instruction from the memory while previous instructions are being executed in other segments of the pipeline. Thus multiple instructions can be executed simultaneously. In most cases, okay, computers need to process each instruction in the following sequence. So the first step is fetch from memory, fine. Second is decode the instruction, calculate the effective address, then fetch the operands from the memory, execute the instruction and store the result in a proper place. You see, step number 4 here, FO, fetch the operands from the memory, is a branch instruction, because in this point it has to read the operands from the memory again. Okay, when you have access only once to a memory, then it is a direct part, but when you have anything referring to the memory again, such as the operands, that will create a branch. This is when we have to empty the pipeline. We'll see this in an example. This is our flowchart for a 4-segment CPU pipeline. The first part is to fetch the instruction from the memory, fine, that's the first segment. It fetches, it reads the instruction. The second segment is it decodes the instruction and calculates its effective address. Okay, during this decoding we'll find out whether the instruction is branched or not. If it is branched, then we'll be performing separate steps, but since it's not branched, we're going to go to segment 3 and get the operand from memory. Fine. Segment 4 will execute the instruction, and then whether it is an interrupt or not, again based on this, whether interrupt can also cause branching. Okay, so the branching and interrupt will go to a separate cycle. When there is no interrupt, we can again go to the repetition where the next instruction is fetched. We look at this side of the cycle where we have a branch or an interrupt. Okay, when that happens, we are going to follow interrupt handling processes. Okay, we're going to update it. Okay, and then we're going to empty the pipeline, and then we're going to go back to the instruction again. This is an example. So we are going to consider stages. Okay, and then we have segments. Fine. Segment 1, 2, 3, 4, 5, and so on. These are the stages of the program. So in the first segment, we read the instruction in the first stage. Fine. When we go to the next stage, the next segment, sorry, the first program that was read, okay, is being executed, and we read a second instruction. Okay, so these stages refer to the instructions. First, we read the first instruction in the first segment. We are going to look at this column wise. This is going to show us each cycle. So the first step, we only read the first instruction. In the second step, we are executing it. Normal computer system would perform all these, and then it would go for the next one. But as we can see in an instruction pipeline, while executing the first instruction, it is already reading the second instruction. Fine. In the third segment, it is reading the operands, fine, from the memory, while it is executing the second instruction, and at the same time it is reading the fetching the third instruction. So you see, this is parallel processing. Fine. We go to the fourth segment where the first instruction has been executed. For the second instruction, we are getting an operand. In the third instruction, we are decoding it, and in the fourth one, we are reading it. Okay, after the execution, over here in the fifth segment, we find out that this is the fifth segment, and we have executed the second instruction. The third instruction is where we find out that there may have been an interrupt, okay, when we brought the operands. Fine. So what is going to happen is the fourth instruction is going to be kept at hold. Okay, this is a branching over here. The fourth instruction will be kept at hold, okay, until the third instruction is executed. Again, in the second segment, third instruction has been executed, fourth is still on hold. Seventh segment, we are going to repeat, copy the whole fourth instruction again and start from the beginning, and then you can see the cycle continues where one instruction is being executed and the next is being read, then another two instructions are executed and the third is being read, and so on. So this is an explanation. So when the instruction is fetched on the first clock cycle in segment 1, that is the instruction 1, and then it is decoded in the next clock cycle, okay, and then the operations are fetched, and finally the instruction is executed. This is the whole step for the first instruction. We can see that when the fetch and decode phase overlap due to the pipelining, this was the overlap that we saw in the reading of the second instruction while the decoding of the first instruction. By the time the first one is decoded, the next one has been fetched. Okay, in case of the third, we can see that it is a branched instruction as we had seen. So when it was being decoded, fourth instruction was fetched simultaneously, but the decoding told us that there was a branching. Hence, we keep the fourth on hold until the third was executed. Once the third completely executed, we copied fourth instruction and went back to the phases to continue as usual. This is it for the arithmetic and instruction pipelining. We'll be continuing with the rest in the next video. Thank you.